the last week of the semester, insane. And here we are with one of the coolest, craziest, most insane topics. And sadly, just a little bit of time to talk about it. But we're going to try to get as much of the coolness of these guys conveyed in the amount of time that we have. And hopefully you'll get inspired to keep studying some more math. These are powerful, and therefore, again, power series is what we're talking about. So where are we? We're at sections 1110 and 1111. We're kind of doing both of them a little bit weaved together. What are we talking about? It's Taylor and Maclaurin series and polynomials. And of course, error, right? We've been doing that for a while now. Okay, error is mostly going to come in a later lecture, but we'll still talk a little bit about all of these ideas. So of these words up here that are underlined, right, Taylor and Maclaurin are the two new vocab words, and so we've got to learn what they mean. Like when we see those, what do they mean? And they're people, and so what do they mean in this context, right? You know what a series is, and you know what a polynomial is, right? Okay, well, let's just review the idea of series, right? That's what we've got going on over here, which you've seen in many videos. So by series, now what do we mean? We mean power series, right? We've graduated from talking about series of adding up infinitely many numbers to now adding up series of infinitely many functions. What types of functions? Power functions, right? An infinite sum of power functions, right? Okay, infinite sum of power functions. So we've upped the ante now, right? Okay, and we've already talked about what those functions look like. They are written succinctly. There's either where we're talking about one centered at 0 or one centered at a, which is just more general, right? So this one is this one when a is 0, right? What are we doing? We're adding up infinitely many terms of constants times powers, right, of x, right? Or powers of x minus a. The constants, the c sub n's, are coefficients, right? And we talked about different coefficients then will give us a different power series, right? We say this in a lot of different ways. We either say a series centered at 0 or centered at a, or a series expanded about 0 or expanded about a, or a series in powers of x to the n or in powers of x minus a to the n, right? Regardless of how we say it, we always mean, what is said there. And again, this is the shorthand version. What is this if we write it out? It's just this summation, right? Just keep on going, right? Constants times powers of x, right? Whereas this one is constants times powers of x minus a. Yes? Right? Okay? So we've been doing that, right? That's reviewing series. And then the question is, well, what's a polynomial, right? Well, it's just these guys where we actually stop, right? Okay? So a polynomial is not an infinite sum of power functions, but it's a finite sum, right? It's a finite sum of our power functions, right? Of our constants times power functions, right? Of our cn's and x to the n's, right? Or our cn's and x minus a to the n's, yeah? Okay, so what would we do? We would have a c0 plus c1x plus c2x squared, right, plus c3x cubed, and then we'd stop somewhere, right? C k x to the k, right? This would be the kth degree, or if we want to stick with n, right, so that we can sum on k, then we have, this would be the nth degree, right, polynomial. Yeah, an nth degree polynomial, right? That nth degree polynomial expanded about 0 is just summing k equals 0 to n. I would stop at n, cn x to the n, right? When n is 0, I get c0, or when k is ck, x to the k, right? All right, stop rushing. Okay. When k is 0, I got c0, x to the 0. When k is 1, c1, x to the 1. K is 2, c2, x to the 2. And then I stop when k is n, right? Okay? So this is a finite sum, right? And similar if it's in terms of x minus a. You would just stop at c sub n, x minus a to the n, right? Okay. So, as you might be thinking, okay, from what we've learned, adding up infinitely many things can be hard, so sometimes we approximate it with finitely many things. So what is the idea of error? The idea of error is going to be, what if we use a polynomial instead of a series, right? We stop, maybe we use a third degree polynomial. We've left off infinitely many terms, right? The remainder. How good is our approximation to the infinite guy, right? That's where we're going with the error. But right now, we haven't talked about Taylor or Maclaurin yet, right? So that's the key now. All of these things, series and polynomials, and error exist without these ideas of Taylor and Maclaurin. So what is the deal with Taylor and Maclaurin? Well, the main deal is these are very special ways to choose the c sub n's. Very special ways to choose the c sub n's. And that's what we're going to explore in just a minute. How do you choose these c sub n's? But why do we have two different names, right? Okay, well, the Taylor guy is going to be like the more general power series, expanded about, centered at A, right? So Taylor is always about some A that's not necessarily, not 0, okay? And Maclaurin is a power series that has a, again, very special way to choose the CN. So that's what it's all about, right? How are we going to choose these CNs? But Maclaurin refers to, this one is about 0, the easier case, right? The case where it's just powers of x to the n. Yeah, does that make sense? And so we want to start creating some Taylor series and some Maclaurin series. And we know what they look like this, but the question is, well, what are they? What do we even mean? A Taylor series or a Maclaurin series for a function, f of x, and how do we choose these coefficients, okay? So that's kind of our deal. We've already seen such an example. So let's, before we dive into how do we choose these guys, let's notice we've actually already seen some examples. Actually, several, okay? So, for example, let's reconsider the geometric series. Remember what the geometric series was, guys? What was that? Sum n equals 0 to infinity of r to the n, right? What did we get? When n is 0, we got 1. When n is 1, r plus r squared plus r cubed, on and on forever, right? Okay? And what did we discover, right? That we discovered that this thing, right, converges when what? Tell me what is true about r. When does this converge? Right? It converges if and only if what? The absolute value of r is less than 1, right? So we have minus 1 is less than r is less than 1, yeah? It diverges otherwise, yes? Nice. And what does it converge to? Good. 1 over 1 minus r. We derived all that with nth partial sums a while ago, right? Quite a while ago. Okay, so we know that. What if okay, what was r here, right? Okay. Create myself some space. What was r here? R is some fixed real number. That's what we were assuming, right? We had some fixed real number and then we were going to add it up, right? Like if r was a half. 1 plus a half squared plus a half cubed, right? Okay? All right. And that nice little formula tells us how to sum that and get 2. Yeah? If r is a half, right? Okay? Awesome. Okay. But what if we replace r with x? This is kind of what math is all about, right? When you go from replacing numbers to letters. Well, this is still a letter, but it's a letter that represents a single number. And this is a letter that represents all possible real numbers, right? Okay, so now we're asking another question, like, what if we were to replace r with x? Well, then we might be saying, hey, wait a minute, is this true? So I'm going to write it the other way now, okay? What if I replace r with x and I start with that formula over there? 1 over 1 minus, we replace r with x, good. 1 over 1 minus x. What would I say that might be equal to? Well, is it true that 1 over 1 minus x is equal to 1 plus x squared plus x cubed, on and on forever? That's one of our questions, right? Okay, which is just, if we sum n equals 0 to infinity, x to the n, right? Replacing r with x, right? What is x? Where x is a variable, right? Not a parameter, not a constant x, not a constant r. X is a variable, and x is an element of the real numbers, right? So we can ask this question about this thing, right? But really, what are we kind of asking? We're asking a couple of different things. We're asking, okay, well, what is this piece equivalent to? We're really asking, what is the interval of convergence of this series, right? What is the interval of convergence? That's from our power series language of this series. It's a power series, right? What are the c sub n's? They're all 1, right? The c sub n's are all 1. 1 times 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, right? Okay, so it's not too hard to use our root test or ratio test to show that the interval of convergence, you should be able to do that for this series, right, is when the absolute value of x is less than 1, which implies minus 1 is less than x, which is less than 1, okay? If we look at the x, that would come from ratio or root test. If you look at the endpoints, which you have to do with the power series, right? If you put in 1 to the n, does 1 to the n converge? No, divergence test, done. This guy doesn't go to 0. Does negative 1 to the n converge if we're summing, right? Sum? No, because this guy wouldn't sum, the divergence test would immediately say that limit isn't 0 and therefore it diverges, right? So we've checked both endpoints. We have the interval of convergence here. And so this series has an interval of convergence minus 1 to 1, just like our geometric series. So our question is this series actually equal to this function? Right? That's kind of what we are. Like, can we use this series for this function? Well, if so, when? Only in the interval of convergence, right? So is that true for x between minus 1 and 1? Well, that's kind of cool, right? There's all kinds of ways that this gets used. We'll talk about that a little bit later. But we've already sort of seen this idea with geometric series. Now we're just sort of upping the ante to say, okay, these aren't really numbers, they're actually variables. And what's the domain of this guy? What's the interval of convergence? For what x's can I do this? And again, I got to add all infinitely many terms, right? So there'll be some more work that we'll have to do to justify this equality, but that's coming a little bit later too. The question is so for this power series, the geometric series, right? the C sub n's are all identically equal to 1. All of them. C0 is 1, C1 is 1, C2 is 1, okay? Can we justify that? Why? Why should that be for this function? So we're about to generalize this concept, right? This guy is a function of x. F of x, 1 over 1 minus x. That's a totally legit function. You've been working with it in calculus for forever. You know its domain, you know its, right, the domain of this guy is certainly different than the domain of this guy, right? Okay, right? Okay, just x not equal to 1 here, right? So you gotta be a little bit careful, right? You can do calculus on it, you can differentiate it, you can integrate it, right? This function. Yeah, but now we're saying, can we represent it as an infinite series and have that infinite series be equivalent to it, right, for at least the interval of convergence? Yeah? So we need to figure out how to choose the C sub n's, right? How should we choose the C sub n's in some very special way so that if we wanted to create a power series that represents a function on its interval of convergence, we could properly do that. Yeah? Okay? So that's the idea of Taylor and Maclaurin series. This would be a Maclaurin series for this guy because it's expanded about 0, right? It's in powers of x to the n, right? If we wanted to expand this about some other number, right, like a half, then we would need a series like this, and you would have to recompute what the coefficients ought to be. So let's try to figure out how to come up with, see if we can come up with a formula for the coefficients in general for a general function f. Okay? That's where we are. That's where we're heading. Yeah? Okay? All right. So here we go. So I'm claiming that that would be indeed the Maclaurin series for that function after we derive how to compute the coefficients, then you can double check that that is really indeed what the coefficients turn out to be. Nothing but ones. Alrighty, this is exciting. Okay, so let's see. Oh, one of the things I forgot to mention, all right. Right, so we had already talked about, so in that previous thing, which we just had, 1 over 1 minus x, right, is equal to 1 plus x squared plus x cubed, right? Right, only for minus 1 less than x less than 1, right? And so, right, if we put in like a half, right, x equals a half is certainly within this range, minus 1 to 1, right? And so if we did that, 1 over 1 minus a half, right? That would give us 2 from this side. Yes? You guys with me there? 1 minus a half, right? We get a half on the bottom, flips up. We can say that that's this. It's our geometric series, right? But note, outside the interval, we talked about it, we just didn't demonstrate it. Outside the interval of convergence, this is bogus, right? Totally not true. That's why the interval of convergence is super important, right? Let's look at x equals 2, right? 2 is outside the interval of convergence, right? So this, it would be totally ridiculous to try to use this as a representation for this when x is 2. Why? What would we get if x is 2? On the left-hand side, we would get -1, right? 1 minus 2, -1. What would we get on the right-hand side? 1 plus 2 plus 4 plus 8. Does that look like that's going to -1? Like, that's insane. Absolutely no, right? And so this interval of convergence, critically important to pay attention to. These guys get used as approximations for these guys all the time, especially in engineering, okay? And if you're outside of an interval of convergence, you're blowing things up, you're having stuff crumble underneath lots of people. That's not good. All right? Okay. Okay, so let's see, what else do we want to talk about before we keep going? All right, we're moving right along. So we want to explore all these ideas and generalize them. So what I'm going to do is work on how do we develop what we should choose from Maclaurin series, because those guys are just simpler, right? X to the n instead of x minus a to the n. This one is in your book, okay? So you can read the derivation in your book, okay? We'll derive the CNs now, okay? Once you've seen it for this, it'll be easier to read the derivation in your book, okay? So, here we go. So what do we want? So let's suppose we have some function f of x, okay? And we want that function f of x to be represented by a, well, what are we going to do? We're going to do this one, right? So a power series, right, expanded about 0, right? Or in powers of x to the n, right? So what does that look like if we write it out? C naught plus c1x plus c2x squared, right, plus c3x cubed plus c4x to the fourth, on and on and on and on, forever, right? Forever, yeah? Okay? So let's suppose we have such a thing. Now we're going to have to justify this equality a little bit later, but for right now, let's suppose that this is legit. How should we choose the c sub n's? So that the right-hand side matches the left-hand side. Right? We want these two things to be equal. Here's the right-hand side, the big infinite series, and here's some function, like our 1 over 1 minus x that we just talked about, or e to the x, or sine x, or cosine x, or natural log of 1 plus x. All kinds of different functions, right? Okay? All right, so what do we do? Well, the first thing that you would hope, right, the first thing that you would hope is that you would want the function, and remember, what are we doing? We're expanding about 0, right? So what do we know about this series, right? The whole point of expanding about 0 is that you know the series converges at 0 for sure, and then with the interval of convergence, the question is how far away from 0 can you go in both directions, right? That's the radius of convergence. It tells you how far away you can go, right? Does it only converge at 0? Radius convergence at 0. Does it converge minus infinity to infinity? So you can, radius convergence infinite, can go as far away as you want. Or is there some finite radius of convergence, like with 1 over 1 minus x, our radius convergence is 1, right? Okay? So you know you want this thing to converge at 0. So that says, let's just evaluate both sides at 0, since we know this guy converges for 0, at the very least, then we certainly would want it to match when x is 0, right? So let's evaluate at x equals 0. So first we'll evaluate at x equals 0. Well, that's awesome, right? Okay, what is the left-hand side when evaluated at x equals 0? Yeah, just f evaluated at 0, whatever the function f is, right? Whatever you get out when you put in 0. Okay, and then what is this side when we evaluate at 0? Yeah, right? Put a 0 in for x, right? What are we left with? C0. Oh, okay. Well, look, we found how to, this is how you compute C0. C0 is just whatever the value of the function is at 0. Let's look at a visual, okay? Here's a generic function f, right? Okay? This is my x-axis, this is my y-axis, this is a graph of f, right? What is f of 0, right? So now we're back to like a long time ago, yeah? What is f of 0? Here's 0, right? F of 0 lives on the x-axis, right? Here is f evaluated at 0. It is this, or sorry, lives on the y-axis, right? There's f evaluated at 0. It's this number right here, right? It's just this, for this example, It's this distance away. It's this positive number in this picture case, right? So what should C0 be? C0 should just be that exact thing. The function and the series have to match at the point that you expanded about, right? So if we were expanding in x minus a, then we would care about, if this was a, we would care that f of a was equal to C0. Yeah? Does that make sense? You can check that in your book. All right. So C0 was f of 0. Cool. How do we pick C sub 0? That's what we wanted to know. C sub 0 is the function f evaluated at 0, or some function, right? Okay? Think about what that would mean for our function f of x is 1 over 1 minus x, right? Does that say C0 is 1? Sure does, 1 over 1 minus 0. Okay. Now what? Well, now we have the two sides match at 0. We want them to match more, right? We want them to match more. What do we do in Calc 1? What do we do in Calc 1? What's Calc 1 all about, mostly, right? When we're trying to think about a way to approximate a curvy thing with something not so curvy, or not curvy at all, right? Like a line, right? What kind of line? Yeah, like a tangent line, right? Okay? So suppose what I now want, right? What I now want is to have my function and the tangent line, right, also match up here. So I want what do I do to get a slope of a tangent line? Very nice, I take a derivative, right? Okay, so second, what should I do? Let's take the derivative of both sides, right? Now, again, there's some things we might need to justify, but we'll just go with it. We've skipped section 11.9. We don't have time for it. Go read some fun math things in there. So I take the derivative of the left side, f prime of x, and I take the derivative of that side, and I would want those two series to be equal, right? That would be kind of a nice thing. So what is the derivative of a constant? C0. Good, 0, right? What is the derivative of a constant times x? Awesome, C1, right? Yeah? Derivative of mx plus b is m. Yeah? Okay, nice. All right. What's the derivative of a constant times x squared, right? Constant multiple rule says the constant comes along for the ride, then I take the derivative of this guy. Derivative of x squared is, good, 2x. So what do I get? I stick my 2 out there because that's where I like my constants, right? Okay. Yeah. What's the derivative of c3 times x cubed? Here we go. We're on a roll now. 3 times c3 times x squared, right? What's the derivative of c4 times x to the fourth? Good. 4c4 x cubed, and that goes on and on and on forever, right? Okay? There's our derivative. Also another series. That's 11.9. Anyway, what should we do? What is the slope of the tangent line, right? What is the slope? Oop, that doesn't write real well. Sorry. What is the slope of the tangent line to f at 0? What is it? Not specifically for this f, right? In general, good. F prime evaluated at 0. Yeah, right? That's the slope of the tangent line, right? That's the slope of this line, yeah? Okay? All right, so what does that mean we want to do with this? Evaluated at 0, right? So what is f prime evaluated at 0? Well, we got a 0 there. X's and all that's all going to go away. What are we going to have? C1. Oh, that's kind of awesome, right? Okay, so what does that tell us? C1 should be f prime of 0. Yeah? Makes sense? Our goal was what should we, so far we've got 2 C's. We got infinitely many more to figure out. Okay. So what does this mean visually on this graph, right? C1 needs to be that slope. So C1 is the slope. So visually here, C1 would be a negative number, right? Okay? Okay. Does that make sense? Okay. Now what? What do you think? let's let this roll. How many derivatives can we take? Well, hopefully, if your function has infinitely many derivatives, got polynomials over here, right? That's awesome. I can always take derivatives of polynomials, right? Infinitely many derivatives for polynomials. That's awesome. So now what? F double prime of x, you tell me what that is. Okay, here was f prime of x. So what's f double prime going to be? Derivative of constant is 0, right? So that's going to go away. What's the derivative of 2c2 times x? Good, 2c2. Then plus what? Then I'm going to have my 3c3 times x squared, derivative of x squared, 2x. So that's going to give me a 6c3 times x. Yes? Okay. Plus a next derivative. You guys got it? Good. 12c4 x cubed. On and on. Yep. Whoops. X squared. Whoops. X squared. Bring down the 3. Subtract 1. Okay. Yeah. Good? Okay. Okay. What do I want? I want concavity to match, right? Okay. I want this guy to be as close to that guy as possible for as long, right? Okay. And that's what's happening. That's why the whole terminology expanded about 0, right? We're going to kind of take this thing and come up with a polynomial that approximates this guy as far away from 0 as possible, as best as possible. Yeah? Okay? And if we were in Taylor, we'd just be interested in doing that at some a. Okay? And so we would want this value, we'd want the slope, we'd want the concavity out here, and then you'd be evaluating at a. Okay. But we're at 0, we're doing Maclaurin, so now we evaluated 0. And what do we get? F double prime at 0 is, these guys are 0. Well, at least it gets a little bit different here, right? First it looked like it was just, you always got the constant, but look, we got 2 times the constant. What was our goal? Is find these constants, right? Okay, so if I find these constants, then I need to solve for C2. So what does that mean C2 is? C2 is F double prime at 0 divided by 2, right? Divided by 2, yeah? So that's what C2 ought to be. So what does this mean? In order to find these constants, what are you going to have to be able to do? Take derivatives of your function and then evaluate. We're going to do an example as soon as we keep going with trying to figure out if we can come up with a general formula, right? That was our goal. How do we choose these CNs? We want to try to see if we can come up with a general formula. Okay, so let's keep going with our plan. We know now how to choose C1, C0, C1, and C2, right? Next is we have to figure out how to choose C3. How are we going to figure out how to choose C3? Very good. Take the third derivative. F triple prime, right? What is F triple prime of x? Where do I go to take F triple prime? Oh, here's my F double prime, nicely labeled, right? Yeah? Full mathematical sentence. Yes? Okay. All right. Now I'm going to take the derivative. What is the derivative of 2c2? Good. 0, right? 2 is a constant. C2 is a constant. Product of constants is constants. Derivative of a constant is 0. Yes? All right. What's the derivative of 6c3 times x? Good. 6c3, right? Constant times x. What's the derivative of the next term? Good. 24c4x. Plus on, right? What do we do now? Evaluate at 0. We want the third derivatives to match at the point we're expanding about, right? That's the whole point. Okay, make it match as close as possible. What if I evaluate this guy at 0? What am I going to get? Nice. 6c3, because I'll get 0 and then there's all x's back here, right? Okay. What was I doing? Trying to figure out how to solve for the constants. So what does C3 need to be? C3 needs to be, solve this equation, F triple prime evaluated at 0 divided by 6, right? Okay. Let's do one more. What do we do? Fourth derivative. Maybe we'll even do a few more. Let's just do one more. Let's do fourth derivative. How do we say fourth derivative? We could say prime, right? I even lost count of how many I did, so there's a reason why we don't do that, right? We put some things in parentheses. We could put a 4 up here in parentheses. That would mean take the fourth derivative, right? Without the parentheses, it means f to the fourth power. It doesn't mean take the derivative. So you can't just willy-nilly leave off the parentheses. A lot of times we'll use Roman numerals just for fun, okay? So that's what I'm doing right here, little I, little v, that's 4, okay? Evaluated at x first. We've got to take the derivative first, right? So that's saying take the derivative, take the fourth derivative, okay? That's the same thing as d4f dx to the fourth, right? The fourth derivative of f. And now what? We're going to take the derivative. Here's the third derivative, nicely written out for us. What's the derivative of 63? Good, 0. What's the derivative of 24c4 times x? Good, 24 times c4. And then we didn't write down the rest of the stuff, right? But what are we going to have out here? Stuff with x's. Yeah? Okay. What is our goal to do with this? Evaluate it where? Very good, 0. What do we get when we evaluate it at 0? Very nice. We get all the stuff with x's, go to 0, right? That's what happens. And then we're just left with 24c4, right? That's for evaluating, okay? So what were we doing? We were interested in what should c4 be. So we solved this equation for c4. c4 is the fourth derivative of the function you're interested in creating the Maclaurin series for, right? So we're doing the Maclaurin series for f of x. That's what we're doing right now, the Maclaurin series for f of x. Take the fourth derivative, evaluate it at 0, and then divide by 24. What a random number, 24. 6. What a random number, 6. Okay, so, let's see. Maybe not random, no, right? Okay, what's our goal once we do all this kind of stuff is to kind of see if we can come up with some idea for, well, what about the nth derivative at 0? That's kind of what we care about. What's the nth derivative at 0? Well, that's what would lead us to a formula then for Cn, right? That's our big question, which I erased. How do we choose the Cn's, right? So now I'm just going to get rid of this so I have more space and recap us where we are. Recapping. How do we choose the C0? Is f evaluated at 0, right? What is C1? F prime evaluated at 0, right? What is C2? F double prime evaluated at 0 divided by 2, right? What is C3? F triple prime evaluated at 0 divided by 6. What is C4? The fourth derivative of f evaluated at 0 divided by 24, right? Our goal is to try to come up with a formula for C sub n, right? By observing a pattern, right? Let's think about this pattern. You should be recognizing these numbers, right? What is 6 the same as? So we've got f triple prime of 0 divided by 6 is, very nice, 3 factorial, right? So you start seeing 6, 24, 120, life is good, right? What is 24 the same as? So I've got the fourth derivative of f at 0, that's my numerator, denominator is 24, 4 factorial, right? 4 times 3 times 2 times 1, right? 4 times 6, 24, very nice. Okay, well tell me about this guy. Is this following the pattern? This is f double prime at 0 divided by, is 2 the same as 2 factorial? Yes, indeed it is, right? 2 times 1, right? What about this guy, right? F prime of 0, is that the same as that divided by 1 factorial? Yes, indeed it is, right? I think we're getting there. Okay, what about this one? F of 0, should have left myself more space, sorry. F of 0, is that the same as f of 0 divided by 0 factorial? Can't divide by 0. Good, 0 factorial is 1. Yay, everybody's happy. All right, and so let's see, how do these guys match up? Can we come up with a formula? How does this number relate to this number, right? Number of derivatives and the guy in the denominator. Not so hard, right? What is it? Cn, this number is the same as that number. So it's the nth derivative, got to have the parentheses, evaluated where? At 0, right? Divided by what? These numbers are the same, right? So divided by n factorial. Woo-hoo! We just said in order to do a Maclaurin series, we have to derive the C sub n's so that we know what to put in there to have a series that approximates the function or that is equal to the function on the interval of convergence, okay? And this is the special way to choose the CNs, okay? There's still some more to prove that they're actually equal, but that'll be a little bit later, okay? Similarly, so let's recap that. So for the Maclaurin series, of f of x, f of x is the sum, n equals 0 to infinity, of the c sub n's. What of our c sub n's? The nth derivative at 0 divided by n factorial. That's our cn's times x to the n, right? For the Taylor series of f expanded about a, what will we use? It'll be the sum, n equals 0 to infinity. Remember, so these guys are our CNs for our Maclaurin series. CN for Maclaurin series. Maclaurin just means expanded about 0. So you never forget to evaluate that at 0, right? These guys are numbers. It's not functions of x. You saw that, right? For a Taylor series, how's that going to change? Well, you're going to need the CNs for the Taylor series, and then it's going to be multiplied times, right? It's a power series in x minus a. So instead of x to the n, you'll have x minus a to the n. A will be given to you, right? And how do the CNs change? This is what's developed in your book. You can read this, but you should understand now where it came from. It's just going to be the nth derivative of the function, right? But this time evaluated where? Good. Not at 0, but at a. Good. Divided by, indeed, n factorial. Okay? All right. So now we want to go compute one of these series, right? We want to start computing some Maclaurin series. Your book does a variety of examples with Taylor series and Maclaurin series. Also notice if we just wanted to compute like a Maclaurin or Taylor polynomial, right? Then what do we mean if you were asked to compute the third degree Taylor polynomial for a function f, then what would the third degree Taylor polynomial be? It would be up through the third order coefficient. So you would just need to determine C0, C1, C2, and C3, right? So that's simpler, yeah? If you just need to determine the polynomial, polynomial is a finite degree. A series is infinitely many, right? Okay, does that make sense? So if you just want the polynomial or the first, several non-zero terms, right? Then you just compute these coefficients until you have enough terms, yeah? Okay? All right. Now we're about to do an example. Maclaurin series for f. Okay? And again, the equal to still have to prove. And it's only valid for our interval of convergence. Okay? Of the power series. Right? And that's our power series. Alrighty. So let's see. Where are we now? Okay. Let's look at an example. So now, right, you could go back for our f of x is 1 over 1 minus x from the geometric series guide, compute the coefficients, right, in the exact same way we're about to do this example for a different function right now, and justify to yourself that, yes, indeed, for that series, the Maclaurin series for f of x equals 1 over 1 minus x, all the coefficients turn out to just be 1. Now, if all the coefficients turn out to be 1, what does that mean? The nth derivative at 0 ends up being? Good. It would have to be n factorial, right? Because then you'd have n factorial over n factorial, that would cancel it, and then you would just get 1, right? Okay, nice. All right, example. Let's look at 11.10, number 12. Okay, so our guy f of x is the natural log of 1 plus x. All right. We want to find Maclaurin series. And let's find the radius of convergence and interval of convergence as well. Okay? Okay. So what's the deal? We want our function f of x, right? Which is natural log of x. Sorry, natural log of 1 plus x. Why can't we do a Maclaurin series for natural log of x? If you're going to expand about x equals 0, right? Then would that work if we had natural log of x? Think about it. Does natural log exist at 0? No way. All right. Anyway, so that's why you get natural log of 1 plus x for a Maclaurin series. This is used quite a bit, okay? Natural log of 1 plus x instead of natural log of x. All right. So what do we want? We really, we just want, just to make sure you don't get too, caught up in this looking super nutty and crazy, right? What does it really mean, right? It just means I'm looking for a power series. And what are the coefficients, right? But now we know how to choose the C sub n's. What are the C sub n's? The C sub n's are the nth derivative evaluated at 0 divided by n factorial, right? That's how we choose them, okay? So, what do? Okay? So, the first thing that you do is you're like, okay, here's my deal, right? I've got to acknowledge what my function is, yeah? Okay? What's my function? My function f of x is the natural log of 1 plus x. Yeah? That's where I start. And then what do I got to do? I know that what I'm going for is this, right? These are my C sub n's. That's what I need to compute. It's the only thing unknown up here, right? The only thing we don't know is what those guys are. How am I going to compute them? I need to start taking derivatives, right? So let's just take a bunch of derivatives, right? Calc 1, yay, okay? So what is the derivative? So take some derivatives. That's what you're going to start with. So what is f prime of x? If f of x is natural log of 1 plus x. Good, it's already there. 1 over 1 plus x times the derivative of the stuff. The derivative of the stuff is just 1, right? So it's just 1 over 1 plus x, right? Now I'm going to take another derivative. F double prime, right? So just takes a bunch of derivatives first. Okay, well, hold on here. Do I want to do the quotient rule? No. Okay, so how do I want to rewrite this guy so that it's easier to take its derivative? Good. Quantity 1 plus x to the negative 1. Yeah? Way simpler. Okay? Now let's take the derivative using that formula and no quotient rule needed, right? So what do we have? Minus 1 plus x to the minus 2, right? Yeah? Now, I'm just taking derivatives, so I don't really even need to rewrite this as minus 1 over 1 plus x quantity squared, right? There's no point in that. I'm just going to take derivatives. It's in a nice form for taking derivatives, right? So what's the third derivative? Yeah, good. Minus and minus 2, so it gives me a plus 2 times 1 plus x to the negative 3. Good. What's the fourth derivative? Yeah, good. Minus 6, 1 plus x to the minus 4, right? Bring down the power, leave the stuff alone. Subtract 1 from the power, multiply by the derivative of the stuff. But what's the derivative of stuff? Just 1. We love that. Yeah? Some of your problems aren't so simple, right? So you can see how the derivative piece could get messy. Yeah? All right. Let's take some more derivatives. What's the fifth derivative? Right? Fifth derivative is 24. Ooh, you're seeing these numbers again. X to the negative 5, right? Okay. So pretty soon you just stop even writing those numbers and you just start writing factorials. But we'll just write them just one more time. What's the sixth derivative, right? VI, right? Roman numerals, okay? What's the sixth derivative? What do we got? Minus 120, 24 times 5, right? Times 1 plus x to the negative 6. Yeah? Let's just do one more, right? Okay. So we could do VII if we want, or we could say the seventh derivative just to make sure you kind of get that. Okay, so what do we have? Plus, okay, we'll just do this one. We'll do the math here, or the arithmetic one more time. But again, we generally aren't going to do that. We're just going to recognize our factorials. But it's 720. Let's just make sure we recognize our guys. 600, 620, 120, 720, right? That is what number factorial? Good, I heard it. Okay, so we took a bunch of derivatives, yeah? There we are. Now let's evaluate derivatives. Where at 0, right? For Maclaurin. If it's a Taylor series expanded about A, then you evaluate the derivatives at A for the Taylor series. Okay? So what are we going to do? What's f of 0? It's the natural log of 1 plus 0, right? So it's the natural log of 1, which is, good, 0. And then what's f prime of 0, right? Let's just start blowing through evaluating. What's f prime of 0, right? 1 plus 0 to the negative 1, that's 1. What's f double prime of 0? It is minus 1 plus 0 to the negative 2, that's just 1, right? Yeah? 1 over, right? That's minus 1 over 1 plus the quantity x squared. When I plug 0 in there, I just get minus 1, right? Third derivative. What do I get? Evaluated at 0. What do I get? 2, right? Fourth derivative. Evaluated at 0. What do I get? 6, right? Which we just said is 3 factorial, right? Okay. Oh, whoops, I don't get 6, I get negative 6. Oh, so let's hold off a second. All right. Negative 6. Fifth derivative evaluated at 0 is positive 24, right? One more sixth derivative evaluated at 0 is negative 120. Now our goal is to come up with a formula for the nth derivative evaluated at 0, right? That's our goal. And we do that by looking at our pattern that we've developed here and to see if we can come up with a general formula based on the pattern, right? So, what do we got? we've got this guy is minus 3 factorial, right? This one is, good, 4 factorial. This one is minus 5 factorial. Well, this looks like an alternating series, right? Or alternating series when we put the numbers in, but alternating sequence right here. So what is 2 the same as? Good, 2 factorial. What is this? Minus 1 factorial, right? What is this? 0 factorial, right? Yeah? So we're starting to see what's happening there, yeah? And so we just want to try to match things up with our notations. Now let's notice, right? Since f of 0 is 0, what do we know, right? C0 is just f evaluated at 0, right? Now let's make sure we understand this notation in fact. So C0 is f, the zeroth derivative of f, evaluated at 0, right? So C0, if I put a 0, divided by 0 factorial, yeah? Okay? What is 0 factorial? Good, 1. What is the zeroth derivative of f? Well, that means take no derivatives of f. So that just means the function f at 0, right? And what is f of 0 for this function? For us, it's 0, so we don't even have a C0 in this problem, right? So for this problem, right, C0 is 0. Yeah? Okay. All right. Now, let's just look at these guys, right? So let's see. I've got the second derivative, I've got 1 factorial. Third derivative, 2 factorial. Fourth derivative, 3 factorial. Fifth derivative, 4 factorial. Sixth derivative, 5 factorial, right? So the number of the derivative is, right? Well, really probably it's better to think of it this way. The number of the factorial over here is, compared to that, 1 less, 1 less, 1 less, 1 less, 1 less. 0 factorial, first derivative, right? So this guy is, if the number of the derivative is n, this guy is n minus 1 factorial, right? Yeah? The factorial is 1 less than the number of the derivative, yeah? Okay, now we got to deal with the alternating sign, right? We know how to alternate sign. It's just minus 1 to the n, or minus 1 to the n minus 1, or minus 1 to the n plus 1, right? We just have to figure out, and the last two I just said, n minus 1 and n plus 1 are the same. It doesn't matter which one you use. We just have to figure out, what do we want? So we want, when n is 1, that's the first derivative, we want positive. When n is 2, we want negative. When n is 3, we want positive. 4, negative, right? So when n is even, I want negative, and when n is odd, I want positive. So what should I use? N or n plus 1? Good, n plus 1. Or n minus 1. I think your book uses n minus 1. I'm just going to use n plus 1, just say it doesn't matter, right? Okay, double check. Let's suppose n is 5. Well, what I have, 5 plus 1 is 6. That would make this positive. Yes. 5 minus 1 is 4 factorial. Yay. Okay, are we good here? Okay. So that's very nice. We now have our general formula for our fn's, right? And therefore, we can write down what our general formula for our cn's are, right? Cn is just what? The nth derivative at 0 divided by n factorial, right? For our Maclaurin series. What did we just discover that is? We're going to plug this in up here, right? So that, for this problem, for the natural log of 1 plus x, is, what am I going to put in? Minus 1 to the n plus 1 times n minus 1 factorial. That's my fn's of 0. My derivatives of the function f evaluated at 0. I have a nice general formula for that. And then I divide by n factorial. Now, the nice thing is, if I only asked you for, like, you know, the up through the cubic polynomial, right, then you don't have to come up with this generic formula, right? You just compute these guys and then compute the first, you know, C0, 1, 2, and C3, and then you're done, right? But if you want the entire series, then you need the general formula. Yeah, does that make sense? Okay. Okay, so does this simplify, guys? Does that simplify? We are factorial cool, right? So how do I want to write this so I see how it simplifies? when my minus 1 to the n plus 1 comes along for the ride, who do I want to rewrite? Good, my n minus 1 stays the same, n minus 1 factorial, because I can rewrite n factorial how? Good, n times n minus 1 factorial. That's what n factorial means, right? This guy times every guy one less. What cancels? Woo-hoo, I see it right there. So what am I left with? Lo and behold, what are our CNs for the function f of x equals natural log of 1 plus x? The CNs are minus 1 to the n plus 1 divided by n. Yeah? Okay? Minus 1 to the n plus 1 divided by n. That's awesome, right? Okay? So now I know them all. Let's just write the series. On the interval of convergence, once we prove something else, but what is it equal to? It's the sum. Well, notice our C0 is 0, right? So this is obviously for n greater than or equal to 1, right? N equals 0 wouldn't make any sense, right? We already said C0 is 0. So our sum for natural log is going to be sum n equals 1 to infinity of what? Minus 1 to the n plus 1 over n. Those are our CNs, right? Times x to the n, right? Power series, Cn x to the n, right? Which, if we just write it out, is when n is 1, what do we have? Right? When n is 1, what do we have? We have x, right? Even 1x. When n is 2, what do I have? Whoops. Minus, right? Minus what? X squared over 2. Yeah? When n is 3, what do I have? When n is 3, this is even, so it's going to be plus x cubed over 3, right? So another way that you might actually prefer to look at this is the sum n equals 1 to infinity minus 1 to the n plus 1 x to the n over n, right? Because that's what we're seeing here, right? Okay, we just kind of slid that, fraction math. So what are we going to have, right? When n is 4, this is odd, so we'll have a minus, right? And then when we have n is 4, it's x to the 4th over 4, right? Plus x to the 5th over 5 minus. That is our series. That is the Maclaurin series for the natural log of 1 plus x. So if we want an infinite series expanded about 0 that is the same as the natural log of 1 plus x, in the interval convergence, let's talk about what that is, then this would be it, right? We still have to do something with the error in the remainder to really prove the equality here. But there's lots of other things that are super important here. What is the best linear function that approximates natural log of 1 plus x near 0? X. What is the best quadratic function that approximates natural log of 1 plus x near 0? X minus x squared over 2. What is the best cubic function that approximates natural log of 1 plus x near 0? X minus x squared over 2 plus x cubed over 3. Right? Okay? All right, so this would be like a third-degree Taylor polynomial. The rest is the remainder, the error in using this polynomial to approximate this function. Polynomials are nice, right? Polynomials are nice. They're easy to integrate. They're easy to differentiate. A lot of times, for many different applications, you'll use a polynomial approximation to a function instead of the function even when you know the function, especially in computation. There's lots of places where this stuff gets used, so you actually need to know something about how much error you have when you don't use infinitely many terms, right? That's what we'll talk about a little bit more next time. For that, we're going to need a general formula for this nth derivative. So let's just, for fun, right here, do that general formula, right? The nth derivative evaluated at x, right? Evaluated at x, so now it depends on x, right? Okay? The nth derivative evaluated at x for the natural log of 1 plus x. We can come up with a general formula for that. What did we say? You know, this guy is 720 is, right? 6 factorial. What is 120? 5 factorial. What is 24? 4 factorial. What is 6? 3 factorial. What is 2? 2 factorial, right? What is 1? 1 factorial. So if I want the nth derivative, right? Then what do I have? What's my factorial? 7 at 6, 6 at 5, right? My factorial is then minus 1 factorial, right? Then what do I have? 1 plus x to the negative n, right? And then I'm going to have an alternation going on. When it's n is odd, I want positive. When it is even, I want negative, right? So same thing, n plus 1, right? So if n is 7, 7 plus 1 is 8, it'd be positive, right? So what is that? That's minus 1 to the n plus 1 times n minus 1 factorial divided by 1 plus x to the n. Now, we may use that later, okay? All right. We didn't need that for what we just now did. All we needed was the general formula when we evaluated at 0. All right, so let's talk interval of convergence now, right? Okay. So we have our nice Maclaurin series, right? Which is equivalent for Maclaurin series for f of x equals natural log of 1 plus x, right? And that's the same as the Taylor series expanded about 0. That doesn't make sense, right? That's a lot more words, so that's why we say Maclaurin series. 4. So when a is 0 for f of x equals natural log of 1 plus x, right? Okay. All right. So let's just look at our series, okay? So we have natural log of 1 plus x. I'll rewrite it one more time. Sum n equals 1 to infinity minus 1 to the n plus 1 x to the n over n, right? So before, in section 11.8, you're just given this piece, right? Find the interval of convergence of this power series. Now, what's super cool about that is, hey, you know what? That's actually the function natural log of 1 plus x. As long as we're in the interval of convergence, and as long as we show that the remainder goes to 0. Okay, so anyway, let's look at the interval of convergence. Interval of convergence, radial convergence of this power series. So remember, we expanded about 0. Okay, you know something about the domain of the natural log of the domain of the natural log function, right? Are we going to be able to get out to -1? Absolutely not, right? So you already know, right? This guy doesn't even exist. Natural log of 0 doesn't exist. So you know that you should never expect convergence, right, at -1, right? Or that this would be equal, yeah? Okay, so we already kind of are expecting that this is not some infinite domain of convergence, interval of convergence. All right, so let's look at this guy. What do, right? I'm going to do the root test. You can do the ratio test for yourself, see if you get the same thing. I think the root test is simpler, right? What is it again? It's the root test for absolute convergence of this power series, right? Where's the power series? It's right here, yeah? Okay, what am I going to do? What does the root test do? It says take the limit as n goes to infinity of the absolute value of all this stuff, right? What is the beauty of having this -1 alternator, right? When we take it absolute value, it just becomes 1. So as long as this guy is -1 to the power, then it's just gone in here, okay? If it's -5 to a power, then you got to split it out as -1 to the n plus 1 times 5 to the n plus 1. But if it's -1, it's gone. You don't bring it along. You don't bring it along in your ratio test either. That's silly. So now what do we have? This guy in absolute value, and then we take the nth root. Yeah? We're going to do this fast now because we've done this 1,000 times. At least I feel like we have. I know it hasn't been. But we can, n is positive, right? X could be any real number, can be negative, so the absolute values have to stick with the x, right? So this is the same as the limit of the absolute value of x to the n over n all to the 1 over n, right? if we now take the nth root, we haven't taken any limits yet, we take the nth root, then on the top, we just get absolute value of x. We love that. And on the bottom, we get into the 1 over n, and we love that. Why? That goes to, what does that go to? Good, that goes to 1. Good, we proved that, right? With, this is infinity to 0 indeterminate form, with using logarithm L'Hopital's rule. We proved that goes to 1. We love that, it's super simple. That means this result is the absolute value of x, right? We're doing the root test, we're looking for convergence. So what do we want to come out of the result to have convergence? We want that to be less than 1, right? Less than 1 for convergence, for absolute convergence, right? Okay. What does that mean? What is the same as the absolute value of x less than 1? Minus 1 is less than x is less than 1, right? We know we have absolute convergence, right? Where? There to there, right? Absolute convergence, yeah? What else do we know? If that guy is greater than 1, what do we know we have from the root test or the ratio test? Divergence, right? So we know, right, that here, there, we've got divergence. Here we've got convergence, right? And what do we know if the absolute value of x is equal to 1? Nothing, right? Inconclusive. Inconclusive, right? What are you going to do? Use another test. What does that mean? Test the endpoint separately. Right? Just like we've been doing. So let's do that. Isn't this a fun problem, right? This is awesome, right? So, you know, like all of calculus, just all in one problem, right? It's phenomenal. All right, so here we go. Let's test the endpoints separately. We already talked about this endpoint, that we don't think that guy is going to converge. So let's see. Let's test x equals -1. What does that mean we do? It means we put it into the series, right? And look at the series. What does the series become when x is -1? So we have the sum n equals 1 to infinity, minus 1 to the n plus 1, times -1, that's what we're putting in for x, to the n over n. And you're like, oh, it's an alternating series. But is it? What is this the same as? What does the numerator become? You guys tell me. Same base raised to a power, minus 1 to the what? N plus 1 plus n, which is 2n plus 1. Have you seen that before? Did we not talk about that a while ago? What is 2n plus 1? Always odd, right? What is -1 raised to an odd number? Always odd, always -1, right? And so what is this guy? -1 over n. What is -1 over n? This is a constant multiple of what? The what? What is 1 over n? The constant multiple is -1, right? So we can think of this as -1 times 1 over n. This is a constant multiple of the, good, you've been screaming it out there, harmonic series, right? And what do we know about the harmonic series? 1 over n, right? 1 over n is a p when p is 1. What do we know about p series when p is 1? The harmonic series, it diverges. Right? So since the harmonic series diverges, a constant multiple of the harmonic series diverges. Right? So as expected, right, that guy is out of our interval of convergence. Okay? What about x equals 1? I'm just going to do this with changing colors, right? Make my life simpler. Sorry. At least you can stop the video, unlike in class. Test x equals 1. Now what happens, right? Then we're just plugging in a 1 for x, right? So now what do we have? Now what do we have? Minus 1 to the n plus 1 times what? What's 1 to the n? Just 1, right? So what is that? Well, that's just n equals 1 to infinity of minus 1 to the n plus 1 over n. Have you seen that alternating harmonic series. And what do we know about the alternating harmonic series? It converges conditionally, right? Which means it converges, right? Does not converge absolutely, right? Because the absolute value is the harmonic series, which diverges, right? This converges conditionally, converges but doesn't converge absolutely. By what? Yeah, the alternating series test. Yay, we did that. All right. And so therefore, do we have convergence at 1? Yes, indeed we do, right? Okay. So what is our interval of convergence then? Our interval of convergence here is open parenthesis at -1 and a closed parenthesis at 1, right? -1 is less than x, which is less than or equal to 1. What is the radius of convergence? 1. You can go 1 away, right? The radius doesn't tell you what happens at the endpoints, right? Just tells you up to, okay? All right, how do we use that, right? So as long as we're within the radius of convergence, right? Like when x is 1, then we could, for example, say, okay, well, what if I replace natural log of, what if I replace x with 1? I'm in the radius of convergence, right? Then that says this is 1 minus 1 squared plus 1/3 minus 1/4, right? Plus 1/5, right? Okay, there was a problem that had you look at this a while ago and say, hey, the natural log of 2 is equal to that. We can say that alternating harmonic series converges to the natural log of 2, and here's why. Right? But remember, we can also do some crazy rearrangements because it's conditional convergence and get all kinds of crazy other things, right? But what if we use like a half, right? Then we would have had a half. Whoops, I probably shouldn't. That would have been plus minus a half. Right, so that was x to the 1, x squared, right? X cubed, right? X to the 4th, right? X to the 5th. If we use x for a half, then we're golden that the natural log of 3 halves is that series which you could simplify, right? Okay. So now that gives us ways to sum all kinds of crazy series if we have convergence results and Maclaurin or Taylor series, so we can see what series would converge to. That's super cool. There's so many super cool things. I gotta wrap this video up here. I'm just trying to see what else I ought to say before we finish. Let's see. Make sure, so you should be able to kind of do this same thing that we just did for our 1/1 minus x guy that we started with class with. And you also, we're going to then start talking a little bit about what happens if you're using approximations, a polynomial instead of the infinite series, and how can we actually really justify that this equality is legit in that interval convergence. We've got to look at the remainder if we took a polynomial, finite, right, sum, and show that that remainder goes to 0. So that's all coming up. Plus, a few other things are coming up. I might save that for another video. So maybe, yeah, we'll see. All right, other fun things that we can do with these guys, and in the next video, I want to make sure we have a whole slew of these guys, understand where they come from, and how we can exploit them. All right, that's it for today, or for right now. See you soon.